We continue our discussion of the fermions, specifically the Fermi distribution. Okay. So Fermi distribution, for us, this is the occupation fraction, occupation probability, I'm sorry, which was 1 over e to the power beta epsilon minus mu plus 1. It also has the name of sigmoid function, and specifically what's interesting, this is the occupation probability as a function of epsilon. Here we have mu, which we call Fermi energy, or Fermi level. And we know, which is exactly 1/2, and we know that this function has two specific limits. So in a limit of very low temperatures, it's almost a step function. Okay, this is in the limit of low temperatures. In the limit of high temperatures, it is almost a flat function, which is a uniform distribution. Anywhere in between, it is a transition between those two limits. Now, when we develop this, notice that it only depends on temperature, the chemical potential, which is the Fermi energy, mu. And those two limits are most important. Why? Because what we know is in the limit of very low temperatures, the only levels, although we have 3 levels in our system, but we consider them as independent, so we can look on each level separately, and we say the level is going to be occupied, meaning full, if the energy is lower than the Fermi level, and in the limit, and it's going to be empty, so the probability is almost 0 there, when the energy is higher than the Fermi level. At the high temperatures, I don't care about the energy at all, okay? And any level have exactly the same probability to be occupied, 1/2. So it's either occupied, either not occupied. It's not enough because it's also the same situation holds everywhere, but the probability of being occupied is 1/2, independent of the energy at all. Now, what we can do and obtain with this Fermi level, so usually we can say, well, the temperature, I have a control over the temperature. So T, the temperature, is something that I can control. I can heat up the system, I can set my thermometer. But how I control the Fermi level, okay? iPhone? No, it's fine, because it was in the denominator, I cancelled out. All right. Now, for the chemical potential mu, the question is how I can control it. Okay. Because, well, we studied till now many systems where we had some sort of control of the temperature. How we control mu. And this is, or how we can even calculate mu, right? Because I'm saying, well, we have different energetic levels, those epsilons, there's different levels inside the system, right? So this is the energetic spectrum, energy, and we have different levels. I pick up a specific level, okay? This is my specific level, and the only thing, at least at the limit of low temperatures, I need to see if it's above or below the Fermi level. If it's below the Fermi level, I'm saying, well, it's going to be occupied for low temperatures. If it's above, it's going to be empty, right? But can I control mu, or at least how I can calculate mu, right? So usually beta and mu, as we know, those are the parameters, but the parameters I should control, right? The occupation probability, whether the specific levels are occupied or not, is an outcome, but T and mu is my control over the systems. So how can I control T and mu? The problem is it's really difficult to control the Fermi level. Temperature, I can heat it up. How I control mu? And the answer is, well, since it's difficult to control mu, we should control something else. And this something else, control over the average number of particles inside the system. Now notice something funny. I decided to tell you the development of this grand canonical potential. So all of this is grand canonical potential. Ensemble, I'm sorry. And all of this development for the grand canonical ensemble is that I don't have a constant energy and I don't have a constant number of particles. Now we hit a wall with mu because we don't know how to control it. I'm suggesting to control the average number of particles. But it's a little bit reasonable, right? So I'm saying, well, I don't know exactly how many particles are inside, but I can get a number of what is the average number of particles, okay? And by looking on this average number of particles, I can somehow maybe get a control over mu, okay? Because what is mu? What is the chemical potential? Chemical potential is how much energy I have to pay in order to introduce new particles inside the system, okay? Now, instead of saying I can control this specific energy, I would just say, well, I can control how many particles in total that could be inside the system. Okay, I can prevent from particles to coming in or getting out, and this is the way to control this average number. So let's see how it works. At least in the level of small temperatures, how it works. This claim, how it actually gets me to understand what is the value of mu. So I would be working in the limit of low temperatures, because in the limit of high temperatures, mu is irrelevant, right? Because the occupation probability is almost all 1/2. So we are working in the limit of low temperatures. In our system, again, we have epsilon 1, and epsilon 2, and epsilon 3, okay? And I'm saying the following thing. I will calculate the average number of particles as a function of mu. Average number of particles. Average number of particles. As a function of mu. It will get me some specific expression. And after I will get this expression, I will say, well, actually I know what n is, or I can control it somehow differently, and from this expression I will get the value of mu. Okay? So instead of setting mu and seeing what happens inside the system, I obtain this number, and then I'm saying I know what n average is, and out of this equation I will get expression for mu. Okay? So this is what we're going to present now. Okay, so how to compute it? So let's start. What is n average? So n average, it is what? The probability we have to go over all the different levels. We have 1, 2, 3 different levels inside our system. Okay. And we want to ask the following. So it is what? So if I want to see what is the average number of particles in level epsilon 1, what it's going to be? The average number of particles at level with energy, which is epsilon 1. So I know it's either 0 or 1. Let's consider first the situation when I'm looking on particles with spin up. Okay, so for this specific energetic state, okay, it's either one particle occupies it or non-particles are occupying it. So it is n of epsilon 1 with spin up. It's going to be 0 multiply the probability that no particles are occupying it, which is 1 over epsilon minus beta epsilon 1 minus mu plus 1, okay, plus the probability, or plus 1, a specific particle is sitting there, multiplied by the probability it's actually occupied. What is the probability that it's occupied? E to the power minus beta epsilon 1 minus mu divided by e to the power minus beta epsilon 1 minus mu plus 1. So we obtain the expression for a given specific state. The average number of particles there is what? Is just 1 multiplied by 1 divided by e to the power beta epsilon 1 minus mu plus 1. So exactly this occupation probability that we plotted over here is also the average number of particles that is sitting in this specific state, epsilon 1, with spin up. Okay. The total average number of particles is what? I have just to sum over all the different states in the system. What are the different states? Energetic states. Epsilon 1 spin up, epsilon 1 spin down, epsilon 2 spin up, epsilon 2 spin down, epsilon 3 spin up, epsilon 3 spin down. So the total average number of particles is n epsilon 1 spin up plus n epsilon 1 spin down plus n epsilon 2 spin up plus n epsilon 2 spin down plus n epsilon 3 spin up plus n epsilon 3 spin down. Each of those contributes according to what I have written over here. The only thing that differs is the expression of the energy, right? It's independent of the spin up and down. Okay, this is our degeneracy. So we're getting 1 over 1 plus e to the power beta epsilon 1 minus mu plus 1 over 1 plus e to the power beta epsilon 2 minus mu plus 1 over 1 plus e to the power beta epsilon 3 minus mu.
Isn't it times 2?
Sorry?
Times 2.
Times 2. Okay, so we have 2 over here, 2 over here, and 2 over here. Epsilon 1, epsilon 2, and epsilon 3 are set. Those are the microscopic properties of our system, right? The only thing that it's not set, and this is the parameter, which is beta and mu, beta and mu, and beta and mu. We are operating in the limit of small temperatures, okay? We are operating in the limit of small temperatures. So this is the average number of particles inside our system as a function of mu. Okay. This is the expression. Okay? My parameters are beta and mu, and I'm using them or modifying them in order to compute the average number of particles inside the system. Great. But this is not what I wanted to measure. I wanted to measure mu, and the idea was, okay, control this mu by somehow describing the average number of particles. Now, although we said that the number of particles is not known, we can say the following. If we somehow know, we can control the system such that we know, at least on average, what is the number of particles, okay? So we know what n of mu is. Right? If I know that, at least at the limit of small temperatures, I set up nu to a specific number. Let's choose this number to be 4. Okay? So I have a specific number for the average number of particles. I don't know where they are. Okay? I know that now I've got an expression which reads as follows. I have 4 equals to 2 multiplied by 1 over 1 plus e to the power beta epsilon 1 minus mu plus 1 over 1 plus e to the power beta epsilon 2 minus mu plus 1 over 1 plus e to the power beta of epsilon 3 minus mu. And this is my equation. I assume that t goes to 0, and I'll somehow, out of this equation, I should obtain what? I should obtain mu over here. Okay. This is the idea. Okay.
Where did the 4 come from?
I assume that it's 4. Yeah. Otherwise, I don't know how to solve it. So this is the expression. So I know how to control beta, right? Because it's just a control of temperature. But I don't know how to control mu. And the only way that I can control mu is by measuring and also somehow modifying the average number of particles. Okay? That's the only way. In some sense, you can say it as follows. Well, we use the grand canonical ensemble in order to derive everything, to derive the probabilities. The moment that we have all those probabilities, okay, we are saying, oh, well, actually, I don't need mu as a parameter. I can use n as a parameter, and then to define what mu is. Okay? That's what I'm saying. You're absolutely right. So the assumption of t goes to 0, I haven't used it, okay, so far. The thing is, I don't know how to solve this equation for general t. Okay, it's not a regular algebraic equation, so I need to obtain mu as a function of what? Of the epsilon 1, epsilon 2, and epsilon 3, and t. I'm saying that I will use t goes to 0 because this is probably the only limit where I can somehow solve this. Okay. All right. So how we are going to solve this guy? Now, we are going to use this property. So notice we have here 1, 2, 3. Okay, 3 parts, but each of them, it's this Fermi distribution calculated at a specific epsilon, right? This is the Fermi distribution calculated at epsilon 1. This is the Fermi distribution calculated at epsilon 2. And this is the Fermi distribution calculated at epsilon 3. Now, the thing about this Fermi distribution, 1 over 1 plus e to the power minus beta epsilon minus mu, at the limit of t goes to 0, and only on this limit t goes to 0, as a function of epsilon, you can assume this is the theta function. Okay. This is a sigmoid function. It gets out 1 if you're below mu, and it gets out 2, or I'm sorry, 0 if you're above the Fermi level. Okay? Only in this limit, those sigmoid functions, these Fermi distributions, are operating like this. And this is why I want to take t goes to 0, because when t goes to 0, all right, each of those will contribute as a step function, and it's easier to operate. Because otherwise, I don't know how to solve or how to get out mu when the distribution looks like this.
לא אמור להיות מינוס אבל אם...
Where?
תלוי ב...
No.
אוקיי.
Here?
זה לא פה זה בלי מינוס, פה זה...
Exactly. So there is no minus over here. Okay. So what do we do? We have 4 particles, and we know the following thing. If we have all those 4 particles, we have them, they have to occupy, because of this theta function, they have to occupy the lowest energies, right? We are in the level of very small temperatures, and we have to occupy only the lowest states. So if I plot my states, I know the following. I know that epsilon 1 will have probably 2 particles. One will spin up, one will spin down. And epsilon 2, right, will also have 2 particles. One will spin up and one will spin down. So this is the idea. Alright, so if this is indeed an idea, I can say mu have to be somewhere over here. Where exactly? So if this is epsilon 3, where exactly I don't know. Right? Why this is true? Because if mu was below epsilon 1, okay, according to this prescription of a theta function, I could not have the probability of epsilon 1 to be occupied is 0, okay? So I couldn't have 4 particles inside the system. Right? If the Fermi level was between epsilon 1 and epsilon 2, okay, again, this reality could not happen. Why? Because the probability of having particles sitting at energetic level epsilon 2, again, according to this theta function, should be again 0.
For fermions.
For fermions, only for fermions. We will deal with bosons later. Again, then this reality cannot happen. Okay, so therefore I should push my energy Fermi level a little bit higher than epsilon 2, but again, it shouldn't go above epsilon 3. Why it shouldn't go above epsilon 3? Well, because otherwise it's also going to be occupied. Okay? So the way to work with finding the Fermi level only in the limit of small temperatures works when you use this theta function representation. The moment that you cannot use this theta function representation, you're basically dead. Okay. Okay. So how do I know this? How do I know this? I know this by stating the following. We have e to the power beta epsilon minus mu plus 1. So let's see what is the expression of this guy, okay, in the limit when t goes to 0. Okay. So first, let's assume that epsilon minus mu is greater than 0. Okay. And then we will assume that epsilon minus mu is smaller than 0. So when epsilon minus mu is greater than 0, what I have here, I have an exponent of beta. T goes to 0, beta goes to infinity. Okay, so I have 1 over 1 plus an exponent of a very large number, okay, very large number, multiplied by something positive. So in total, this is an exponent of a very large and positive number. Okay, so 1 here is absolutely negligible, right? So instead of 1 over e to the power beta epsilon minus mu plus 1, I can write e to the power minus beta epsilon minus mu. Right? This is the approximation. On the other hand, when epsilon minus mu is smaller than 0, okay, I have 1 over here, all right? But here I have an epsilon exponent of beta. Beta goes to infinity multiplied by a negative number. Doesn't matter if this negative number is small or large. I have an exponent of large negative number. Okay? So what happens when it's large and negative? Oh, it is 0, right? Is it exactly 0?
No.
No. What is this?
Should get the second order first.
1 plus
So it's a small number. Okay? In total, it's a small number. So I can write it down as 1 minus e to the power beta epsilon minus mu. Okay? So how I obtained this guy? Said that 1 plus x approximately as 1 minus x when x goes to 0. Okay? So in one case, I have a very large number, so 1 is negligible. Okay? In the other case, I have 1 plus very small number. I won't say just 1. I will use something that includes this approximation that have epsilon and mu inside. Okay, so what is my next step? My next step is to use this approximation inside this equation over here. So what do we have? We have, let's cancel 4 and 2, so 2, and here is 2. So I have 2 equals, and let's go for each and single one of those Fermi functions. So let's focus on the first one. So we have 1 over 1 plus e to the power beta epsilon 1 minus mu. Okay? We use the approximation. We assume that the Fermi level is somewhere above epsilon 2. So epsilon minus mu is smaller than 0. Therefore, for the first Fermi function, we write as 1 minus e to the power beta epsilon 1 minus mu. Okay. This is the first Fermi function. We go to the second one. Plus 1 minus, the same idea operates over here. We know that mu is, or we assume that mu is somewhere above epsilon 2. Okay. And if it's above epsilon 2, then epsilon 2 minus mu is lower than 0, and we use this approximation. So it's again 1 minus e to the power beta epsilon 2 minus mu. Okay. Now we go to the third case. And what happens over here? This is the situation where epsilon 3 minus mu is positive. So we use this approximation. Plus e to the power minus beta epsilon 3 minus mu. Okay. So this is supposed to be easier, right? Somehow. So let's see why it's a little bit easier. 2 and 2 cancels out, right? So plus 1, 2 cancels out. And we have e to the power beta epsilon 1 minus mu plus e to the power beta epsilon 2 minus mu equals to e to the power minus beta epsilon 3 minus mu. And now I'm looking on this equation, and I made already huge number of approximations. Okay? And I'm asking myself, is it solvable? So somehow, can I somehow get mu out of this equation?
Yes.
Are you sure?
Factoring to the power beta epsilon.
Okay. So the suggestion over here is e to the power beta epsilon. Okay. What? So what is the suggestion? Take what?
The mu.
Take the mu out.
Yeah.
And what I'm getting? balagan. So I'm getting e to the power minus beta mu, right? E to the power minus beta mu multiplied by e to the power beta epsilon 1 plus e to the power beta epsilon 2 equals to e to the power beta mu, right? Multiplied by what? E to the power beta minus beta epsilon 3. All right. So what we are getting is, let's multiply both sides by e to the power beta mu. Not a good marker. E to the power beta mu. Okay. So what we are getting is that on the right hand side we have e to the 2 beta mu. On the left hand side, undivided and multiplied by e to the power minus beta epsilon 3. On the right hand side, we're getting e to the beta epsilon 1 plus e to the beta epsilon 2. Okay. Therefore, e to the 2 beta mu equals to e to the beta epsilon 1 plus e to the beta epsilon 2 divided by multiplied to e to the beta epsilon 3. Okay, so let's take a log of the left hand side, a log of the right hand side. So log of an exponent on the left hand side gives us 2 beta mu equals to a log of e to the beta epsilon 1 plus e to the beta epsilon 2 multiplied by e to the beta epsilon 3. Okay. Here we obtain that mu equals 1 over 2 beta logarithm of e to the beta epsilon 1 plus e to the beta epsilon 2 e to the beta epsilon 3. It's not very nice expression. Okay? It only tells us, all right, so the temperature is not exactly 0. Okay, it's very close to 0. And then you have some sort of a dependence which includes, notice that it includes all the energies, okay, and it includes all the temperatures. Beta, beta. Now by epsilon 1, epsilon 2 you cannot control, but you can control temperature, and what will gives you, it will gives you how exactly this level is modified between epsilon 2 and epsilon 3. The point of this exercise is that mu will depend on the number of particles, will depend on the temperature, it will depend on the microscopical structure of your system, but it's usually very hard to obtain. The calculation of the Fermi level, it's accessible only in the low temperatures limit, because only then you can convert those guys into something that you can operate with. And even then, notice I could obtain something which was actually nice only due to the fact that I could cancel all the regular numbers, right? So if I had 2 and 1 and plus 1, if it was not cancelable, okay, I couldn't have obtained this trick with beta mu. So the solution usually obtained a not so nice but some normal analytical form only in the limit when t goes to 0. Otherwise, you're stuck. Questions?
Can you operate the limit of t goes to infinity?
Okay, so what happens when the t goes to infinity?
You may take the exponential
To the half.
No, to a linear approximation.
To a linear approximation. So I can do it. But then it's not so interesting. And I will tell you exactly why. Okay? Because in the limit of high temperatures, the knowledge of Fermi level is irrelevant. Right? Because in the limit of high temperatures, this distribution is flat. So you don't care. You just basically don't care what it is. So the only thing when it matters is when you say, oh, some of them are occupied, some of them are not occupied, and this happens only in the limit of low temperatures. When everything can be occupied or unoccupied with exactly the same probability, you have a pure gas of non-interacting particles. You don't care about Fermi level, you don't care about anything. At least in this model, okay? Okay. Any other questions? Yes?
הניחוש שלנו של כמות הממוצעת של חלקיקים חייבת להיות זוגית, יכולה להיות אי-זוגית, כאילו איך אני מחשב?
Alright, so the question, how exactly I calculate what are 2, 3, 4. So I solve this problem at home, and I've seen that I can obtain something which is reasonable, not reasonable, but a closed form expression, only for this specific case when I have 4 particles, alright, and I'm operating in the limit of low temperatures. Okay. There are very few examples where you can solve something analytically. Okay, that's it. So usually, okay, you're not guessing. You're not guessing. You will be provided a specific situation when things cancel out, and then you can obtain a closed form solution. Otherwise, you're stuck. Okay, even if I'll try this with 3 particles, I'm going to be stuck. Okay, that's it. So the whole point is you can solve it somehow. There is always a solution. Usually, you'll have to use computer to find the solution because it's a nonlinear equation. Okay. And you'll have to use numerical methods. Sometimes you can solve it. But the thing is that you do not control mu. You control the number of particles. That's it. That's the whole point. Okay? Yes?
Shouldn't like the expected value of n be not like the whole number?
Why not?
Because we...
Well, yes, so I could put here 3.75. Alright? Could I solve it then? The answer is no. That's it. But you're right. I can put it whatever I want. I can put here whatever I want. Okay. The only thing is that eventually whatever I'm putting over here will result in some crazy equation from you. That's it. Yes.
אם נניח היה לך n שווה 3, אז איך היית מחליט לאן לקחת את הפונקציה בשביל אפסילון 2? כאילו אם לקחת את הגבול שזה חיובי או שלילי?
Alright, so if I had 3 particles, okay? If I had 3 particles, so I know that the lowest energetic levels cannot get more than 2. Okay, so therefore I still had to place another particles over here, okay, epsilon 2, and I know if it's occupied, probably the Fermi level is a little bit above. That's it. It's a guesswork. Okay? It's a guesswork. You sometimes have to guess over here. If you don't want to guess, well, solve this equation exactly, and that's it. You can.
גם אם זה קצת מעל אפסילון 2, זה לא אומר שכל אפסילון 2 צריך להיות מלא?
No. Oh, so reasonable, right? But exactly at the limit when t goes to 0, only in this limit, when t exactly is 0, you have a step function. When t, well, let's look on the function again, on our step function, because this is actually important. So when I'm plotting the Fermi distribution as a function of epsilon, here is my mu. Again, what is this? It is 1 divided by 1 plus e to the power of beta epsilon minus 2. Okay. Now, it is a step function only when when beta is approaching infinity, which is basically t equals to 0. Only in this limit you have something like this. Okay? In any other limit, t is finite. Okay? It's 0.00001 kelvins. Right? What it will mean? It will mean that it goes as 1, 1, 1, and then you have small deviations. Right? You can say the deviations are unimportant, but maybe they are. The thing is that the only thing that you care is this guy over here. Exactly at mu, no matter what your beta is, exactly at mu, you have 1/2. Okay. So you have deviations from 1 and deviations from 0 only in a specific limit around this mu. Okay. And around this mu, this function is decaying exponentially. So it's decaying exponentially towards 0, or it's approaching exponentially. It's like an inverse exponential decay towards 1. What is the decay of this function? The decay is always k Boltzmann t. So what we can operate is that when your epsilon equals exactly mu, if you're exactly at the Fermi level, right? The Fermi distribution is always 1/2. You shift a little bit, it goes a little bit down. You shift a little bit to the left, it goes a little bit up. But if you shift more than what? You shift your energy more than k Boltzmann t to the right, or more than k Boltzmann t to the left, your function will approach the other one or the either of the two limits, either 1 or 0. So what you're saying is, well, the only thing that matters is the Fermi level, and a region of order of 2k Boltzmann t around it. Only in this limit of 2k Boltzmann t, something happens. If your energies are mu plus 3k Boltzmann t, you're already at 0. If your energy is mu minus 3k Boltzmann t, you're also already at 0. This is the only your dynamical range. And if your temperature is very, very, very small, you always have to only care about small region around this mu. Okay? So for fermions, due to this presence of a step function, you only care about mu and some region of order of k Boltzmann t around it. Okay? Those are the energetic levels that are relevant. If you have very low energies, they're occupied. If you have very high energies, unoccupied. Always. You look on the Fermi level, okay? You look on the Fermi level, and you look on k Boltzmann t around it. That's it. This is why the high temperatures are not so important. Why? Because at high temperatures, when this k Boltzmann t is huge, well, everything is half. Any other questions before we solve something which is actually a little bit more physical and relevant? Yes.
We are dealing with a grand canonical ensemble,
yes,
where n is varied.
Exactly.
So you found mu, and you're generally going to find mu as a function of n and the energy levels. But n is not fixed, and the energy is for a state, but mu, isn't it supposed to be a
other way around?
function of the
Yes,
system?
yes, you're absolutely right. The point is as follows. We developed everything where we assumed that we have two parameters that we can control. Beta, which is the temperature, and the chemical potential, right? The problem with this approach, eventually, is that we cannot control mu. We can't. But, so we have all those beautiful mathematical expressions, right? We can solve those guys and those and some other examples as well. But eventually, right, you want to go to the experimentalist and tell him, all right, I have this and this effect when temperature is 7 Kelvin. He says, great, I can do a 7 Kelvin. And you say, well, and the Fermi level in the system have to be 2.7 k Boltzmann t. And then he says, well, what? And then the answer is, it's a true conundrum, right? Because I cannot control mu. It's usually something that is stuck in the system. But what I can control, there is a connection, right? Eventually, there is a connection between the number of particles, the average number of particles, and mu. If I set everything, I set the microscopic structure, so I set all the different energies inside my system, and I set the temperature, okay? There is one-to-one correspondence between mu and n. And if I somehow can control n, this means that I control mu. Right? This is the idea.
Is it the assumption you assume that you can't control n?
No, no. The assumption is that mu, the moment that I have all the parameter sets, it defines a specific behavior, it defines n, right? Now physically, I cannot control n, but mu, but I can decide what n is, somehow, right? This means that mu have to be exactly such that n is what I set. So usually you take a system and you let it be, right? You say, I have some specific beta and I have some specific mu. And then the system at equilibrium will settle to a specific state. In this specific state, there is going to be an average number of particles, like in my example, 4, right? If I'll take mu, like this one, and I set a very low temperature, I will get this situation. What I'm saying to you is do the opposite. Do the opposite. Set temperature, set the number of particles such it is exactly 4, okay? And you will get this mu. Okay? So I'm switching the roles of what is the variable and what is the parameter. At the point that there I have one correspondence, I don't care who is the variable and who is the parameter. I haven't broken anything. I've developed a final equation using the notion that beta and mu are the parameters. Okay? I set all the parameters except mu, and I switched roles. I mathematically can do it, and physically can do it, therefore it has to work. And it works. Think about it. Think about it. Okay. I want to continue. Think about it. Okay? Okay, so... Wow, we spent too much time on this. I want to solve something which is actually a model that works. And I will explain why it works. It's called Fermi gas / liquid. And the idea is as follows. If we have a metal, okay, and in this metal there are electrons, and the conduction of those electrons are produced by the free electrons that sit inside this metal. The question is, okay, what is the behavior of such a system? Now usually we can say, well, the electrons, they interact with each other, and they interact with the medium, etc., etc., etc. But the idea of Fermi was to say, but what will happen in a system, okay? What will happen in a system where let's forget about the interactions. So let's throw out all the different interactions between the particles, which are electrons, right? We'll throw them out, and the only thing that we never cannot throw away is the Pauli exclusion principle. Okay? So I have free electrons, free, non-interacting, quote unquote. Why it's quote unquote? Because, well, the Pauli principle, the Pauli exclusion principle is still there. Electrons. Now it's basically, I'm assuming that each electron can have spin +1/2 and -1/2. Now this will introduce some degeneracy inside the system. Okay. Now the electrons are absolutely free. So if they are absolutely free, the energy of each state, again, not electrons, because the grand canonical perspective is look on the levels. So the different levels in the system is p squared divided by 2m. Okay? So I have a continuum spectrum inside my system, okay? This is the energy. And it starts from 0 and it goes up. And it's very, 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 very dense. They're not interacting, so there is only kinetic energy. Okay, there is only kinetic energy, and I know that this energy is provided to me by epsilon p squared divided by 2m. So it is h bar k squared divided by 2m. Right? H bar squared. Okay, so then all those different states, not electrons, all the different states are not interacting, okay? And I can say that let P cup a specific K, this is my wave vector, okay? Let's pick up a specific state with a specific spin, okay? And we can write down for this specific state the partition function, the grand canonical partition function. Now each state, because those are fermions, can be either occupied or unoccupied, okay? And we already know this because we solved it for the previous problem, that the partition function is 1 plus e to the power minus beta epsilon or h bar square k square divided by 2m minus mu. This is the partition function for a specific state, meaning a specific energetic level. And this is the partition function of this specific energetic level. All the different levels are independent. Therefore, the z is what? The partition function is a multiplication of all possible k's and all possible s, okay, of zks. Now, notice that the partition function depends on what? On k, but it's independent of s, okay, like previously. So therefore, it is a multiplication of all possible k's, okay, of 1 plus e to the power minus beta h bar squared k squared divided by 2m minus mu to the power of 2. Why the power of 2? Because of the s. This is our degeneracy. So this is the degeneracy because zk 1/2, zk minus 1/2 is exactly the same. So this is the degeneracy. Okay. Great. Now, if we want to compute something, this is the partition function. We have it. If we want to compute something, what I mean by something, let's take the grand canonical potential. The grand canonical potential is minus 1 over beta log of z. Okay? So we have minus 1 over beta log of what? Log of a multiplication over all possible k's of 1 plus e to the power minus beta h bar squared k squared divided by 2m minus mu to the power of 2. So finally, we have minus k boson t as sum over all possible k's from 0 to infinity, basically. Of what? Of 2, we have 2 over here, of a logarithm of 1 plus e to the power minus beta h bar squared k squared divided by 2m minus mu. Now, there is some specific problem. What is the problem? I don't know what k's are possible and what k's are not possible, etc., etc., etc. So how do you think I should compute this sum? The idea is, well, different K's, sit over here, are dense enough. So exactly as in the bimodal, I should take this summation over K and translate it into integration over K. Over K or over energies, but some sort of integration. So integration either over K or over epsilon. What is epsilon? The possible energies that I have inside my system.
Stas, why you need 1 over beta became K volts on T?
Because what is beta?
1 over K volts.
And I have 1 over beta.
Ah,
Okay. Okay. Here, if I want to make this transformation, I should have to remember d omega as the density of states that I have inside my system. Okay. D omega, d omega. Now, I don't want to operate exactly of d omega, but we'll see it in a second. Now, what is this d omega over here? So, when we were talking about this metal, right? We're talking about electrons that are sitting inside a box. Okay, it can be a wire, whatever. We know that the volume of this box is V. Now, what we have done in the Debye model, we said the following. Eventually, the only thing that matters, and this is how the quantization came in, is that there are specific boundary conditions, right? And those specific boundary conditions impose specific density of state. So not all possible wave vectors can survive. Now, the same happens here, right? Because what is an electronic state, or energetic state, is some specific electron that lives inside a system. Now the electron does not escape. So if the electron does not escape, we have to solve a Schrodinger equation inside volume V, inside a box. Now what Schrodinger equation that has absolutely no potential inside the volume V, right? And the particles cannot escape outside, so think about it as an infinite potential on the edges. What it produces?
Sine and cosine.
Sine and cosine. So it produces waves. The solution of the Schrodinger equation, okay, without any potential, is always e to the some power, basically sine and cosine. But it's not just some sine and cosine, those specific sine of cosines, because of the boundary conditions. Because the boundary conditions, well, the electrons are not getting out freely outside of the box. They're locked inside, right? So, as in the bimodal, we looked on this different density that came up of the different sine and cosine, which are just stable waves, non-decreasing, non-decaying waves that live inside the box. The same happens over here. So we can write down that d omega is the volume divided by 2 pi, right? I don't remember exactly this expression. 2 pi squared. K squared dk d omega. Yes. Okay.
Again, why are we looking at the Schrodinger solution? Why?
Electrons. Electrons
Electrons.
described in quantum, they're fermions. So what kind of equation describes their motion?
Okay, so we moved from the potential, from the grand canonical potential.
No, we haven't moved. We're still in the grand canonical potential. But you have to supply any physical problem with what is the physics. And the physics is, well, I have this energetic spectrum, and I have particles, and I told you that they are fermions. Okay? The problem is I cannot solve K, okay? Because I don't know exactly what K's are possible or not. I'm assuming that they are dense enough. I'm going to this integral. And in integral, I know that all the different states are coming from solutions of Schrodinger equations that is described by sine and cosines. Okay. So volume we know, 2 we know, pi hopefully we know, k squared, dk and d omega. So how we connect k and epsilon. So I don't want to go into, so I know the following. Epsilon is h bar omega, as I know. And I also know that h bar squared, k squared, divided by 2m equals to epsilon. Okay. This means that the following. So I have to compute 2 volume divided by 2 pi squared multiplied by k. So let's get k out of here. What is k?
2m.
Actually k squared. So k squared equals to 2m epsilon divided by h bar squared. All right, so we have 2m epsilon divided by h bar squared. Okay, this is the k squared. Now we have dk over d omega. So I want going to write it down as dk of d epsilon, d omega. Fine? Okay. So what is d epsilon, d omega?
H bar.
H bar. What is dk to d epsilon? So we know that k squared equals to 2m epsilon divided by h bar. So k is a square root of 2m epsilon divided by h bar squared. All right. So dk
2m divided.
is square root of 2m by h bar squared multiplied by 1/2 multiplied by 1 over square root of epsilon. Okay. Is it enough? Or we have forgotten something? This is the density multiplied by d omega. The omega over here, right? So, in order to compute this guy, we also have to multiply it by what is d omega. And d omega d epsilon equals to h bar d omega. Okay, so now we know everything. Okay? Everything, I mean by everything, all the different constituents of the sum. So what we have? We have that the grand canonical potential equals to minus 2 k Boltzmann T. Instead of a summation, we have an integral. Okay? Wait a second, we will write down what are the lower and the upper limit of this integral. Now, after this, we have this guy. Now, but we don't want to work in the k space, we want to work in the epsilon space. Right? So, what we have is a log of 1 plus e to the power minus beta epsilon minus mu, okay, multiplied by this, or this. Let's write it down in some other marker. V divided by 2 pi squared, 2m epsilon divided by h bar multiplied by a square root of 2m divided by h bar squared multiplied by 1/2 multiplied by 1 over square root of epsilon, and instead of d omega we have d epsilon divided by h bar. This is our grand canonical potential. Okay. Okay. So let's take everything that is not epsilon related out of here. So psi equals 2. We have minus 2k Boltzmann T. This is still related. We have volume divided by 2 pi squared. This is 2m h bar squared. Okay, square root of 2m divided by h bar squared multiplied by 1/2 multiplied by 1 over h bar. And inside we have a logarithm of 1 plus e to the power minus beta epsilon minus mu. Okay, and finally, what we have? Square root of epsilon d epsilon. Okay, so the integral is not that bad, but we forgot something. And what we forgot? The limits, right? It's a specific something. Okay, the limits. What are the limits? So it's a kinetic energy. So kinetic energy cannot be smaller than 0. Great. Do we have an upper limit? No? Why mu? So if you have a gas of particles inside a box, okay? Oh, they are fermions, which is okay. But eventually it's a gas of particles. Is there some limitation to the possible energies, okay, that can be to this gas?
They can't pass the speed of light.
Forget about the speed. Speed of light is infinite, okay? Quantum mechanics here. Speed of light is infinite, okay? So, infinity. In the Debye model, there was some specific constraint. The constraint came from what? From, well, this is in a continuum, there is some limits over here. Here we don't have this constraint. So it's from 0 to infinity. Okay, so let's look what are these different prefactors. What we cancel can cancel. 2, 2, 2. So it's still k Boltzmann T v, it's still the same. Pi squared still the same. So we have minus k Boltzmann T v divided by 2 pi squared. This is fine.
You cancel it.
What?
You cancel it.
2, 2,
But
2.
there is two.
There's another one.
Another.
So no. 1, 2, 3. So 1 stays over there.
No,
The
there is
middle.
In the middle, in the brackets, in the bracket. No, I want to do with the brackets the following thing. I want to do with the brackets 2m divided by h bar squared to the power of 3/2 multiplied by 1 over h bar. It's nicer. What I have in my conspects. Seems okay. Okay. All right. H bar squared. Okay. And here we have an integral from 0 to infinity of log 1 plus e to the power minus beta epsilon minus mu epsilon to 1/2 d epsilon. Okay, now what we want to compute. Remember, the only interesting quantity somehow is the Fermi level. Okay? Because in the limit of low temperatures at least, what we know that all the states up to the Fermi level are going to be occupied, and all the states above the Fermi level are unoccupied. And in general, we have a k Boltzmann T range around mu Fermi, a little bit above, a little bit below. So anything that happens around mu Fermi. Okay? So the first thing to compute is to compute mu Fermi. If we know what mu Fermi is, we can understand what happens next. So what is mu Fermi for this system? Again, the question comes right. So no, mu Fermi is a parameter. How you can compute the parameter? I do again the switch that I told you about. I will compute the average number of particles and then switch the roles. So what is the parameter and what is not a parameter? Okay. So the idea is let's compute the average number of particles. What is n? So what is n? How we compute it? How we compute n? How n is related to the grand canonical potential? Do you remember what? Okay, a derivative. So f t is e minus ts minus mu n. Okay, this means that d psi to d mu minus equals to an average. Because this is here an average. N is not the exact number of particles when we're looking on thermodynamics. N is the average. S and T, Ts is the average. Okay? So we have to take this guy and take a derivative out of it with respect to mu. So let's see what happens.
Why is the epsilon is the שורש ולא מינוס 1 of the שורש? אפסילון.
היה עוד...
There was another epsilon.
צריך פעם למעלה בשתיים מהם אפסילון.
Here, you have here, yeah. Okay. So what is d psi to d mu with what? With a minus. So d psi to d mu equals to, so we still have minus k Boltzmann t divided by 2 pi squared 2m divided by h bar squared to the 3/2 1 over h bar. Now we have to take a derivative of psi. Now with mu, so the mathematicians close your eyes. I'm saying that the derivative of mu is just a derivative of whatever sits inside. Okay, so it's still an integral from 0 to infinity. The derivative of the logarithm with respect to mu is 1 over 1 plus e to the power minus beta epsilon minus mu. Okay, the inner derivative of this guy is e to the power minus beta epsilon minus mu multiplied by beta, right? Just by beta, multiplied by epsilon to the 1/2 d epsilon.
I think the second thing because it's a multiplication.
Of what?
The line is multiplied by epsilon in
It's a 1 over, and then the inner derivative is just the exponent, and the inner derivative is just mu.
Yeah, we do a derivative by mu, not by epsilon.
Exactly. The derivative is with respect to mu. Okay. Now we have a minus sign over here, so we have a plus sign over here, and this is n. Okay. Beta cancels out, so we have 1 over, well, we have v somewhere, so we have v. So v divided by 2 pi squared, 2m h bar squared, 3/2, 1 over h bar, an integral from 0 to infinity of epsilon to 1/2, e goes down, so we have e to the power beta epsilon minus mu plus 1 d epsilon. And in a second, you will realize why I write it exactly like this. Okay, so this is what we have to compute for any temperature. Okay, for absolutely any temperature. Okay. Okay, this is the average number. But again, we want to operate in the limit of small temperatures. T goes to 0. Okay? Yes. Okay, so in the limit of T goes to 0, what is this guy? It's a step function. It's a step function. This is the Fermi distribution. Okay. Well, I don't know how to solve exactly this integral, right? It's like before, I have some connection between n and mu, and it's difficult, and I don't know exactly how to solve it. In the limit of small temperatures, I can somehow do some sort of a magic. It's not exactly magic. And the approximation always involves something that's about this Fermi distribution. Now, I know that it's a step function. So it is 1 for any epsilon below mu Fermi, and it's 0 above mu Fermi. So all of this is what? It is an integral between 0 and mu Fermi of epsilon to 1/2 multiplied by 1 the epsilon. That's it. Okay? Okay. So what we have over here, so let's solve it. So the solution of this guy is 2/3 of epsilon to 3/2, right? Between 0 and mu Fermi, which is 2/3 mu Fermi to the power 3/2. Okay. So the average number of particles is V divided by 2 pi squared multiplied by 2m divided by h bar squared 3/2 1 over h bar multiplied by 2/3 mu Fermi to the power 3/2. This is an explicit connection between the mu Fermi and the number of particles.
That's why we substitute for the Fermi distribution the step function, not just.
So you want to approximate it. So what will happen, say, it's not exactly a step function, it's something plus something small. Okay? So this is the leading order, and you have corrections. Okay? You're right, you have corrections. Let's forget about those corrections for a while, okay? Because I want to make a point. There are corrections, you're right. Because it's not a step function, it's step functions plus something. So I'm going to get a mu Fermi to the power 3/2 plus corrections. Those corrections have to go to 0 as the temperature goes to 0, okay? But there are corrections, okay? But the point is that I can calculate mu Fermi, okay, out of this equation. So out of this equation, mu Fermi, the leading order of mu Fermi, there are small corrections as you said, mu Fermi is what we have over here, n divided by v multiplied by 3 multiplied by h bar multiplied by 2 pi. We want to pi over here, pi. Okay, now we have pi squared. We already have 2m divided by h bar squared to the power 3/2. And all of this to the power of 2/3. this is our mu Fermi. This is the mu Fermi. Now, the general question is, in this, again, we switch what we control. We want to compute mu Fermi, and we control everything else. What is n to the v? It's in the order of 10 to the power 22. It's a big number, right? We have many free electrons in our gas. So n divided by v is extremely large number. Okay? Well, we have the mass and the h bar, etc., etc. The point is, when we substitute everything, inside, what we obtain is mu Fermi. Okay, it is some number, let's call it A, multiplied by K Boltzmann. Okay. Why I say K Boltzmann? In order to set the units right. So it's energy. So mu Fermi tells me what is the energy of the system, but I want to write it down as some T effective multiplied by K Boltzmann. This A, the effective temperature, multiplied by K Boltzmann. Why I want to do this? Because all the particles are free, right? All the particles are free. And I can measure the energy by some specific K Boltzmann T. This is the average, this is the average energy or kinetic energy of the system. Now, when I measure this in this terms, T effective is on the order of 10 to the 4 or 10 to the 5 Kelvin. Okay. So what we obtained is, because n divided by v is large, mu Fermi is also large. Okay? In the limit of small, very small temperatures, mu Fermi is also large. Okay? So, now, you can say, so what? You calculate some specific mu Fermi, we don't exactly understand what this chemical potential is, and you calculate that it is extremely large. So what? But this is very important, because what happens, even in this limit of small temperatures? What happens in the limit of very small temperatures? We know that all the states, all the energetic levels are occupied up to mu Fermi, okay? And then you go a little bit above mu Fermi, okay? Or you go a little bit below mu Fermi, and then there is some range where there are unoccupied states. So if you plot the energy, okay, so here is 0, and up there in the sky is mu Fermi. So mu Fermi is on the order of 10 to the 4 or 10 to the 5 multiplied by K Boltzmann. So we know that all the energetic states are absolutely occupied. You don't care about what happens to the low energy states. They're occupied. So it's not the electrons are piled up on top of each other. But when we're looking on the energetic spectrum, everything is occupied. Everything is occupied. And now only at the level of energies, free energies of what? Kinetic energies, all right? When we are talking about 10 to the 4 K Boltzmann, there is some range when there are unoccupied states, okay? Only in the range of remember, mu Fermi plus minus K Boltzmann T, those are the energies which can be unoccupied and then occupied. So the dynamics happens only in this range. Okay? Now mu Fermi is 10 to the 4. So we know that in the range of 10 plus minus, or 10 to the 5, plus minus the temperature of the system, multiplied by K Boltzmann, only here the system can go, or some unoccupied energetic states or occupied energetic states. Now, why it's important? Why I pile up all the different states on one of each other? Because you remember what we started from. We started with, let's assume that electrons are operating as if there are no interactions between them. Okay? We throw away all the different interactions that we had in the system, and we only saved the Pauli exclusion principle. And the Pauli exclusion principle tells us that, well, all the states are going to be occupied up high over there, and eventually, okay, you have some range where some dynamics happens. Now you can say, Stas, great, you solved the problem, but what about the interactions? Okay? Some of the particles are going to be interacting with each other, right? It's great that you solved the gas. What happens where there are interactions between the particles? And the answer is, the interactions are not important. Due to this solution, so because what? So Pauli exclusion principle is stronger than any other interactions. So if I want to affect the system, I want an interaction that should be of the order of this mu Fermi that I have over here. All the different interactions between the different electrons are much lower than mu Fermi. So they're ineffective. The result over here for this fermion behavior is that Pauli exclusion principle piles up all the different particles up to a very, very high energetic level. If you want to include interactions, this won't matter anything because you have to operate on the level of mu Fermi. So as long as your interactions are less important or smaller than mu Fermi, you can throw out all the interactions. So as long as n divided by v is very, very large, your mu Fermi is going to be also extremely large, okay? And the interactions are not important. Okay. Yes?
What about high temperatures?
High temperatures, you don't care. So, how high? This is your limit. If room temperature, right? So 10 to the 5 to 173. Who is larger?
We have temperatures like 5,000. Like
yes, so when the moment that you're going to plasma temperatures, yes, something breaks down.
That's when you have white dwarfs.
Yep, yeah. Everything breaks down when you have extremely high temperatures. Okay? But you have to go, this is your limit, 10 to the 4, 10 to the 5. Okay? Because only then you're operating on the level of the Pauli exclusion principle, and only then you can do something. Otherwise, well, it's a small addition or of something at the mu Fermi level. All right, so thank you all. This is it for today. I'm sorry that I've taken another 5 minutes of your time. כן.
אמרת שמיו פרמי פלוס מינוס כמו בולצמן T זה מה שאפשר,
אתה זוכר שציירנו
מה
את זה ככה?
שנשאר אחרי
סתכל, זה ככה.